Hi, and welcome to Mr. Hamilton's Math Bites. This video is about geometric series. A geometric series is simply a geometric sequence with all the terms added together. So for example, let's take the geometric sequence 1, 7, 49, 343, etc. You can clearly see that in each case I'm multiplying by 7. And so if I just take the value, the comma really, and I replace it with a addition sign, I now have the geometric series as shown. This is the sequence. This is a series. Now, notice I could also actually have a series where I start at -1 and I subtract 7, I subtract 49, and I could subtract 343. In that case, you'd be multiplying every value by 7, but you're starting with an a value of -1. Whereas over here, you're starting with an a value of 1. So, how do we calculate values using these series? Just going to let that be a minus dot dot dot. Well, I won't derive the formula for you. You can see the derivation in, I'm sure, whatever textbook you have. You can also see the derivation on other videos that someone's posted online. But I'm going to get to using those and show you what they are. The first thing that we need to know is the sum of a geometric series can be given by the following formula. Another way to write that would be this: Tn plus 1 minus T1 all divided by r minus 1. Now notice that the Tn plus 1 is the term after the last term. T1 is the first term, and r is that common difference ratio. And then, of course, as we've had always, n is going to be equal to the number of terms in the sequence. And Sn represents the sum. Over here, a is that first term. R, the common difference ratio. And n is the number of terms. I could have just written them in between both, but I didn't think about that until I started writing these out the second time. So there you go. Writing them out twice is always a good habit, and it helps to solidify some of that in your brain, right? Anyway, so now we can use these two formulas to solve equations that have a series that is a geometric series. So here's the first example that I'll give you in light of this. At a fish hatchery, fish hatch at different times even though the eggs were all fertilized at the same time. The number of fish that hatched on each of the first 4 days after fertilization was 2, 10, 50, and 250 respectively. The pattern continues. Calculate the total number of fish hatched during the first 10 days. Now notice this applies to something like marine biology, and even that is using math. Also notice respectively, down here, respectively, that applies specifically to the order being the same. So anytime you want to say that in mathematics, that the order was 1, 2, 3, 4, you could say respectively. And that means the order that you've listed them is the same order that they actually occurred. Alright, so what do we do with this information? Well, the first thing I know is that my first value, my a value, is 2. And then I'm going to go up by a multiple of 5, and then a multiple of 5 again. So these are multiplied by 5, by 5, by 5 yet again. And so what I need to do here is I recognize the r value is 5. And what I'm trying to find is for the first 10 days. So that means the n value is 10. And so I'm trying to find s of 10. And so this is a relatively simple and straightforward situation because I just substitute the numbers into the equation up above. The one on the left side is the one that will work here. I'm going to scroll down a little bit and do that. So Sn, I can find my cursor here, Sn is equal to a times r to the power of n times minus 1 divided by r minus 1. And so we're calculating S10 for the first 10 days. And so the first day 2 fish were born, and then every day after that we had 5 times as many fish. Raise that to the power of 10 over the 10 days. Minus 1. Divide that by 5 minus 1. And what we're left with is 4,882,812. That seems like a lot, but I'm going to go back and write this out in a second. Let's conclude this first and say, therefore, there were 4,882,812 fish born over the 10 days. Well, why in the world is this actually the case? Let's scroll down a little further and talk about why this is the case. In the case of day 1, we had 2, and day 2 we had 10, and day 3 we had 50, and day 4 we had 250. You continue multiplying this by 5, what you get is some big numbers very fast. 1250, multiply that by 5, you get 6,250. Multiply that by 5, you get 31,250. So that's day 7, and then day 8, 31,250 times 5 is 156,250. Day 9 is 781,250, and day 10 is 3,906,250. And so you can see that that last day is almost as many as in total because it's been growing by 5 times. So the last day is far more than was born any other day. And that's the thing we need to keep in mind with anything that's geometric or exponential. The second example looks at selecting a strategy when the number of terms is not known. And this is similar to what we did in the arithmetic series, but it can be a little bit different because in this specific case, we don't actually need to know the number of terms, as we'll find out in a minute. So the first thing I know about this series is that the first term is 7,971,615. The second term is 5,314,410. And so using those two terms, if I go T2 divided by T1, 5,314,410 divided by 7,971,615, that gives me 2 over 3. And so that is the R value. That means R is 2/3. So we know what R is, we know what A is. And so I can pull out those two equations that I know. One of those equations is A times R to the n all minus 1 divided by R minus 1. And the other one is this. Sorry, that's a minus. Let me just correct that. And so those will both work. In the first equation, I know the A value, I know the R value, I don't know the N value, and I don't know the sum. In the second equation, I know the T1 value, I know the R value, but there's a very simple way to determine that Tn plus 1 value. And here's how. We know what the last value is. This is Tn. But Tn is equal to 92,160. We also know that R is 2/3. So T of n plus 1, which means the last or the term after the last term, that must be 92,160 times 2/3. Well, you'd be absolutely correct. It's 61,440. And so we can now use the second equation even though we don't know how many terms are in the sequence. So the sum of the terms, and we're going to keep that as n because we don't know n, is going to be Tn plus 1, which is 61,440, minus T1, which was 7,971,615. Divide all of that by 2/3 minus 1. And when you make that calculation, we can do that over a couple of steps here so you don't make errors. Two-thirds minus 1 is the same as negative 1/3. And then you can flip it and multiply. Multiply by the reciprocal in this case. So that gives me negative 7,910,175. And I'm now going to multiply that by the reciprocal of negative 1/3, which is negative 3/1, or just negative 3. And so the sum of those terms is 23 million, it's a big number, 23,730,525. And we can conclude, therefore, the sum of the terms is that. Now, some of you may wonder, well, how many terms are actually in the sequence? And we absolutely could have found that as well. I'm going to write this in black in the middle here, or red, for example. I could have used this. And I could have solved for n, but we would have had to use a logarithm. And that's absolutely doable. You guys know how to do that. But one of the things we want to do with math is find the most productive and most efficient way to get the answer. And so while this would have worked with this equation, and you're welcome to go ahead and try that, this method that we use was the quickest method here. And there you go. Those are a couple of really good examples that encompass the major concepts of series or geometric series.